I'm Nathan Armentrout.
I'm Justin Clark.
I'm Adrian Fletcher.
And I'm Jacob Shriver.
And we're the Mavon team.
So as we stated before, we are the Mavon team. So let's first go over what is an MAV. MAV stands for Micro Aerial Vehicles. They're a subset of unmanned aerial vehicles, some of which you may know as Predator and Raptor drones. They're very small, maneuverable, and lightweight, and there are several types of MAVs, including fixed wing, rotary wing, and flapping wing. And some of the applications are for home field and battlefield, specifically in surveillance and reconnaissance. Dr. Lauf is our faculty sponsor. He is a new assistant professor in the CCS department at University of Louisville, and he is from Wright State University. His research is in embedded system design with applications to UAVs and MAVs. The purpose of our project is to develop an optical navigation software subsystem for an MAV having only a monocular camera as input. The system should allow for a user-selectable destination, provide semi-autonomous operation, and be adaptable for flapping wing MAVs. The additional constraint is that it should operate in a closed static environment. Here's our software block diagram representing the algorithm we plan to implement. The first step of the algorithm is to obtain the video feed. The video feed will then be optically corrected to provide video stabilization and undistortion. The stabilization will be provided by Dr. Lauf, and the undistortion will be based on camera calibration parameters. Once the video has been corrected, it will be used as input for the object discovery, object tracking and recognition, and egomotion estimation modules. The object discovery module is used to discover prominent objects in the video feed. It will be used to establish a bounding box for the tracking and recognition module. The tracking and recognition module consists of two components, a short-term and a long-term tracker. The short-term tracker will be used to track the object by updating the bounding box from frame to frame. During the short-term tracking phase, a machine learning model will be built so that if the object becomes occluded, the model can be used to recognize and reinitialize the bounding box for tracking. This process will be used to establish landmark objects in the environment. The egomotion estimation module will be utilized to calculate the 3D translational and rotational motion of the camera from frame to frame. This motion will then be used as input for the 3D reconstruction module. The 3D reconstruction module will create a virtual 3D model of the environment. The model will describe the size and location of detected objects, the current location of the camera, and the target destination if selected. Additionally, it will generate any established landmarks and no-fly zones in the environment. The path planning module will use the 3D model generated by the 3D reconstruction module to calculate a path from the current location to the user-selected target destination. Finally, the graphical user interface will tie all of this information together. It will show both the live video feed and a visualization of the 3D environment model. It will provide a method for user-selectable destinations. Additionally, the suggested navigational output provided by the path planning module will be visualized to provide the user with directions. The modularity of this algorithm will allow for incremental improvement over time. This concept has been tested over this semester as several different discovery, tracking, and recognition modules have been swapped in and out for testing. Over the course of the semester, the object discovery and object tracking and recognition modules have been completed, as shown in green. The other four modules, shown in orange, are in progress. First, let's explain the object discovery module. The object discovery method selected is the active contour method, also known as the snake. Object discovery consists of three main phases. The first phase consists of generating random points on a square to create a contour, and then running the snake algorithm. The snake algorithm seeks to minimize its energy by creating a smooth contour around high contrast edges and features. The internal forces of the snake can cause it to collapse on itself. In that case, we regenerate a random contour again, and this process continues until the snake creates a stable contour around an object, and it is declared discovered. Once the object is discovered, a bounding box is created that encompasses the snake. As stated earlier, the object tracking and recognition module is composed of a short-term tracker and a long-term tracker. The short-term tracker uses Lucas-Canati optical flow to evaluate the difference in point correspondence from frame to frame. The difference, aka flow, allows us to estimate the location of the object. However, if the object becomes occluded and point correspondences can't be found, the module must be able to recover the object once it is back in view. For this reason, long-term tracking is needed. During the short-term tracking phase, samples are gathered both of the object and not the object. When the object becomes occluded, a model is built using the random forest machine learning technique with HAR features and histogram values as object attributes. Once the random forest model is built, a search begins using previously determined sized bounding boxes throughout the frame. This will effectively compare image attributes of the selected bounding box against the random forest model. If the object is found, the bounding box for the short-term tracker will be reinitialized. If not, the object discovery module will be reinitialized.
Okay, now we're going to take you to the full object tracking and recognition system. As you can see, the hat is surrounded by a yellow bounding box. This is because it's being tracked by the system. Currently, it's using the short-term tracker. If you just missed it, the system recovered from an occlusion. Let me rewind that for you. As you watch this time, slowed down, the hand passes just in front of the hat. Once it passes in from the hat, this is called an occlusion. Watch as the blue boxes search for the image. Once it's found, the short-term tracker resumes, and tracking can resume again. Now, the next occlusion we're going to show you, we're going to move into the object. In this one, the object is moved away a little slower. The localized tracking using earlier doesn't work as well. The blue boxes you see are searches for the hat. Now that the hat's found, the short-term tracking resumes once again. This process continues until the lifetime of the object. Another occlusion we're going to show you is the hat moving out of the screen. Once it moves out of the screen, we'll continue to search for it until it comes back. No localized search can be used to find this hat. Well, that's all we have for you today. Thanks for watching.